The next one is by Dr. Anthony Chappaz from the Central Michigan University. So Dr. Chappaz is a trace metal molecular geochemist, and his interests are in exploring how microscale process involving trace elements control macroscale biogeochemical cycles. His research interests aim to characterize the reactions controlling the fate and reactivity of trace elements within modern and ancient environmental systems, as well as engineered matrices. They can be divided into three groups: a paleo angle, modern aspect, and a sustainability focus. So the title of his talk is Advancing the Paleo-redox Proxies by Characterizing Their Speciation.
Thank you, Satish, for the introduction. Can you hear me? Can you hear me?
Yeah, I can hear you.
Okay, excellent.
Yeah, good.
So what I want to focus today is unlike the previous great talks. I designed this presentation to try to convince what I'm going to call the paleo communities to embrace the synchrotron techniques, because unfortunately for this community in particular, these synchrotron techniques remain kind of a black box. So what are paleoredox proxies? An ideal paleoredox proxies is obviously redox sensitive. It should be recorded in environmental archives in a kind of direct way and with a minimum of diagenesis. Ideally, it should be straightforward to analyze, and most importantly, relatively simply to interpret and widely recognized by the community. So for the folks interested in reconstructing the Earth redox condition, this is our toolbox, the periodic table. The story basically started with the main element, carbon and sulfur, concentration and also their isotope ratios. Then a new player arrived in the 90s. It was the iron. And over the last 20 years, many other redox sensitive trace elements have been proposed, developed to identify specific redox conditions during Earth's history. So why do we need paleoredox proxies? To better understand the origin of life, why our blue planet is so extraordinary, and why is it linked to the presence of oxygen. Just for the non-specialists, I remind you the first whiff of oxygen occur between 3 billion and 2.4 billion years old. And we had different stages, and it's only during the Phanerozoic, so only 500 million years ago, that really the life exploded on Earth. So a paleoredox proxy is used to identify a specific redox zone that was occurring in the ancient oceans, either in the atmosphere or at the bottom of the ocean. And it's linked to the mineralization of the organic matter. Everything is about, is it oxic or anoxic? And if we go into more details, we can use specific proxies to refine our understanding of the paleoredox condition to hopefully identify a specific zone that would correspond to a specific biogeochemical processes that occur back in the time. So currently, 95% of the paleo studies are based on concentration. By that, I mean they're going to look at enrichment in environmental archives. And by looking at some different levels, they're going to be able to suggest some possible explanation and potential paleo-environmental condition that was prevalent back in the time. In addition of the concentration, you can measure isotope ratios for some of these proxies, here for chromium isotope. Unfortunately, this approach has some flaws. and some of them are speculation, lack of quantitative information, and oversimplification. And that is tied to our ignorance of the mechanistic processes leading to the burial of these paleoredox proxies in sedimentary archives and their possible isotopic fractionation. So one way to deal with that is to add another parameter. It's going to be the speciation. So today I'm going to try to convince you that studying paleoredox proxy speciation in today's presentation is going to be mostly about molybdenum can add a great value to your research. A little bit of background about molybdenum. It's kind of geochemically unique because it displays 7 redox states. 3 are accessible under natural conditions. And on top of that, it has 7 isotopes, which for isotopic geochemistry studies, it offers plenty of approaches to deal with potential interferences. In addition of that, molybdenum is required for fixing nitrogen by all the eukaryote organisms. The basic mechanism explaining why it has drawn attention as a redox proxy is in a water column where you would have the top oxygenated and the presence of sulfide at the bottom is the concentration of oxygen would be maximal where you have oxygen and would decrease in the chemocline when it transitions from oxic to sulfidic and would be minimal under sulfidic condition. Another feature of molybdenum is the different level of enrichment have been proposed as a way to reconstruct what was the different redox condition. So if we want to use this tool, we need to have a minimum of understanding how it works, and in that case, on how it's buried. In the ocean, molybdenum is thought to be present as molybdenum 6, surrounded by 4 oxygen atoms. And as it enters sulfidic water, we have a thiolation, which means the oxygen atoms are replaced by sulfur atom. And after, it's still kind of mystery. But if I were to summarize, I would say 2 main pathways are being considered. Reaction with iron-sulfur mineral phases and interaction with organic matter. So how can X-ray absorption spectroscopy help us with that? First, I would like to just present some basic feature about what is a spectrum that we can collect. And just to show there are 2 parts in a spectrum, you have the XANES for the near edge structure, where here roughly you can have information about the oxidation state and the coordination chemistry of molybdenum in this case. And you have these little wiggles that after some data treatment can be interpreted to collect information about the interatomic distances, the coordination number, and the type of neighboring atoms. So in the next slide, I'm going to quickly show you some known molybdenum compounds, just to highlight the differences you can observe with the XANES and then with XAF. So here it's a zoom just on the XANES region, and starting with molybdenum, which is supposed to be the main molybdenum prevalent species in the oxygenated ocean. One thing that is striking is this molecule has a tetrahedral configuration, and you can observe what we call a huge pre-peak here. Then, if we move to MOS4, that is thought to be the most predominant species in sulfidic water, you can see this pre-feature is considerably attenuated. Now, another molybdenum 6 species, but in that time in an octahedral configuration. As you can see, the XANES can allow us to even differentiate between the different type of coordination chemistry. And the last 2 standards I want to show you are molybdenum 4 species, MO2 and MOS2. And as you will see, An interesting thing is like when it's molybdenum 4, there's no pH features. And for both cases, either molybdenum 6 and molybdenum 4 compounds, when you have sulfur next to the molybdenum instead of oxygen, the edge, which is like the slope here, like the inclination, is going to be at a lower energy. So now let's look at some molybdenum XANES feature. And without going into the details, this is a Fourier transform representation. And just for like novices, the peak represents the signal from like a certain interatomic distance. So picture like the molybdenum being here. And for like MO4, basically, you have a signal of molybdenum at oxygen at a certain distance. The length of the MO sulfur distance is longer than with oxygen. For like MO3, that is octahedral, we have like different oxygen molybdenum distances and also some signal from like another molybdenum. Finally, for like MO2, but as 4, we have also like different type of oxygen molybdenum distances. And for molybdenite, that is like a well-known mineral, you can see like this is a quite long distance, and it's also easy to like figure out if it's molybdenum because of this MO signal. So after like this brief introduction about like how you can use molybdenum speciation to like better like understand its geochemistry, I want to show you like some work that I recently like contributed with many of my collaborators. And the first one is like to answer about the iron-sulfur pathway. So George Els has like contributed to like advance this field in a tremendous way. And 10 years ago, basically, he came with like this ab initio calculation suggesting that molybdenum could be like trapped with like some iron-sulfur cubane. But the fact is like it's extremely difficult to demonstrate in natural sample. So we had the idea with a colleague of mine, Trent Borlichek, to like synthesize this compound. So it took us a while, and I have to give all the credit to Trent. So after months, I'm not saying months of effort, we were able to bring these samples to the beam. And here what we found. You know, I remind you, like I presented you all the standards, they are at the bottom. And the first thing you can see is like, there's no pre-age. So like, it's no more like surrounded by oxygen, probably just by sulfur. And if we look at the maximum energy, we can try to like determine what would be like the average oxidation state. And in all the experimental product we characterize, it was close to 4. But I want to be clear, it was not molybdenite, because after like we ran like the EXAF modeling, we were able to demonstrate that it was a cubane structure that was similar to like the first molybdenum speciation ever like recorded in oxenic lake. And we think it could be jordicite, which is the amorphous molybdenite. With a former point of mine, we like kind of reproduce the same experimental approach, but with that time with organic matter. Because probably what's happening in natural system is you have a contribution of both these like things. So organic matter is like a well-known substrate for like many trace elements. And what we did, because it was the first like try, instead of going like with like real experiments with like organic matter, we decided to like use like small organic acid representing like some like functional group that can be found in the organic matter. And we ran this experiment under oxy condition, sulfidic condition, and with and without iron. And what we found was spectacular. Here I just want to give you an idea of the different standard and experiment we run, in addition of running like natural samples. And here I won't go into detail, but just look at the wide diversity of signal. I just want also to show you like this Fourier transform of one of those experiments that was with like MO2S2. So it's one of the intermediates that is formed during like the molybdenum thiolation by sulfide plus catechol. My hypothesis back in the time was like molybdenum could be linked with like organic molecule, but via the sulfur atom. I was wrong. Our like data actually show like the bonding occur with like the oxygen atom. And it was the first study that kind of de-emphasized the role of MOS4 in natural system. Now let's look at how we can use like synchrotron techniques to like examine and investigate molybdenum speciation in natural samples, starting with like a study we published with some Canadian collaborator in the Utica shale. So here, this is how probably most of like the great collaboration start. This friend now came to see me after a Goldschmidt conference, and like he showed me this profile, and his first question was like, do you think the high enrichment of molybdenum are because of like blip of anoxic condition, sulfidic condition, or due to like post-depositional, you know, like mechanism? So the answer is both. So first, when we look at the average molybdenum oxidation state, we have something like center around 5, which clearly, like in my opinion, demonstrates the presence of 2 molybdenum phases. And if we look at like the EXAF, what we found is like one pool of molybdenum closer to oxygen 6 is bound to organic matter, while the other, in that particular case, and because of this unique signal here, was due to molybdenite that we attributed to like an evidence of metamorphic, you know, like of post-depositional remobilization. Another study like that we recently like published in last year or 2 years ago was like to look at core samples from like the 083, so from 2 cores collected in what was the Western Interior Seaway, so 80 million years ago. In a previous paper, we had run like what I would call the traditional redox geochemistry approach, and we could not really disentangle in between the 2 cores. But here, like using the speciation, we were able to clearly like demonstrate that the site E099 was like buried under more reducing condition than the other one. And even when we looked at the EXAF, the Fourier transform, you can see like the one buried under more like reducing condition show like stronger molybdenum sulfur signal than it does for like the E006 site. So we interpreted and we were able to refine our interpretation by like identifying like E099 as weakly sulfidic, whereas we consider like E06 as ferruginous. So the previous data I showed you was collected with what we call bulk EXAF. But I've turned my attention now to like micro focus technique. So instead of looking at the whole sample, the idea here is to target specific phases like organic matter or like pyrite or even like the matrix. So recently, like we went to the beam and we analyzed like a sample from the Montney formation. So in addition of collecting the speciation, one of the great features also of that is with the XRF, we can get like really good mapping. And by looking at some count, we can be sure like we target specifically like the zone or like the host phase we want to target. Here's some example of spectrum we collected. And we targeted matrix, organic matter, and pyrite. And for like the first one, I want to like clearly like show you that for like a given sample, depending if you target organic matter, pyrite, or even the matrix, you can have like different molybdenum redox state, which is going to open like, unfortunately, like create probably more complication for like the molybdenum isotopic geochemistry because of the clear heterogeneity present in black shale samples. I want to conclude that talk with like connecting like molybdenum speciation with molybdenum isotope. Molybdenum isotope have been like used now for almost 2 decades as a way to reconstruct like the ancient seawater composition. And while like the assumption behind are relatively straightforward, one thing that is being like always like puzzle the community is this large fractionation observed in what you would call like ferrogenous or like slightly sulfidic condition. We have a huge fractionation and we are not sure why. So to try to answer that question, I run 2 sets of black shale sample at the beam. One is from the famous micro shale, they are Archean sample, and it produced a fantastic Nature paper back in the time where we have this peak that is considered the whiff of oxygen. So I run some molybdenum speciation for like before, during, and after the peak, and compare it with like the molybdenum speciation. And also to check that this Archean shale was not altered, I in parallel run like some sample from the Zaneoga formation, which is in Europe. And I went with that one because it's been metamorphically altered. So like it will tell us if we have some alteration. Let's start with the Zaneoga formation. When you look at the average molybdenum oxidation state, it's mostly molybdenum 4. And if we look at the something we call linear combination fittings, actually it's clearly molybdenite, supporting other evidences that black shales was metamorphically altered. Now, if we look at the macro shale, you can see like, depending if it's like before, during, or after, we have like a different molybdenum oxidation state. And now, if we compare that, first, if we try to like run like the linear combination fitting, here we can see it's mostly like the jordicite, you know, like this experimental iron-sulfur phases we were able to synthesize. And also it's very close to MO603 that we consider to be like an analog of organic matter because of the octahedral configuration. But the big finale is like, we have like a beautiful relationship between like the molybdenum oxidation state and the molybdenum isotopic composition, which could like clearly like open a fantastic opportunity to better interpret and, should I say, like correct the original isotopic composition measure. So basically, like the take-home message, I hope like the paleo community would like do is like, please consider like determining speciation, and for that, just come to like use like the synchrotron techniques, because it will improve your understanding of the geochemistry of the proxy in your given system. And I think most importantly, it will refine your interpretation of the paleo-environmental condition that prevail at the time of deposition. And one thing I want to make clear, because I'm not, unlike most of the previous speaker before, I'm not a beamline scientist. Then I want to make it clear, we couldn't achieve anything without their help. They are essential to our success. So I want to say thank you for all of them. And finally, learning like synchrotron technique can be like a daunting task, but don't hesitate to like ask for help. You know, we are here for you. I mean, I or like any other great speaker of this talk, of this workshop. And that concludes my presentation.
Thank you, Anthony. Any comments, questions? Okay, all right, so we have a couple of questions. So the first one is, let me see, Morrison Nolan. So when doing these synchrotron measurements, is it possible to measure other redox sensitive elements concurrently?
Absolutely. So I decided to focus on molybdenum, but because it was the first one, I have like almost now 10 years of experience with it. But since that time, I had the chromium, uranium, vanadium, and recently, for the first time, I was able to measure like rhenium speciation in Grenoble at the RCF at sub ppm level, which is going to unlock new possibilities. Yes.
Right, thank you. The next question is from Adriana Hyman. So the question is, based on your findings of speciation related to molybdenum isotope compositions, do the previous interpretations hold true?
Do you want like the polite version or? So sometimes it does, sometimes it doesn't. Because like, if you remember in my introduction, I was like stating, and again, it's only engaged me, that some previous work just solely based on molybdenum isotope, I think they oversimplified what would have been like the current geochemical control back in the time. And this is why I think adding speciation would be a great tool to like check that your isotope and enrichment makes sense, or at least if you hesitate between two scenarios, it could really help you decide the one that makes more sense.
Yeah, I think so a combination of techniques, I think, is a great
yes.
Right. Thank you. So let's move on to the next speaker. Thank you again, Anthony, for a great talk.
You're welcome.